Good morning, everyone. Thanks for coming. My name is Ben Marsh. I'm the lead on the developer tools team at Epic. We own things like Unreal Build Tool, Automation Tool, the packaging pipeline, and the internal build infrastructure at Epic. All the really glamorous stuff. Today, I'm going to talk about a lot of the things which are an afterthought when you're starting out a project with UE4. You have a bunch of ideas, hopefully a team that's enthusiastic and ready to go, and then you have to figure out how to get everybody to sit down and work together, like the logistics of actually getting them to work together. If you're really lucky, you get to iterate on that over a really long period of time and figure out all the things that work really well for you as a team organically. And if you're unlucky, you pick something early on and then struggle to fix it later on because you don't have time or resources to devote to it. There's lots of things that go into deciding which is the best solution to you. There's things like the culture of your studio, whether you're scrappy or whether you're risk-averse, whatever tribal knowledge people bring from their previous project they worked on, what works and what doesn't work. There's the fact whether you're working on a box product and you have like a one-off release, or whether you're making a live game that you need to sustain over time. And there's whether you know what the game is from the start and you know that you have a hard content pipeline that you need to get up and running quickly, or whether you need to iterate to find the fun. So I'm going to talk about some of the core workflows that we've developed for Fortnite. But a lot of this is extended to other projects that we've done at Epic. So hopefully, as subjective as it is, there might be some things which are useful for you as well. I'm going to break it down into 3 sections. First of all, I'm going to talk about how we distribute the editor, how we get the editor to our artists and designers, and introduce a tool that we use called UnrealGameSync. Then I'm going to talk about our branching model and how we handle multiple releases being in flight at once on a live game. And finally, I'm going to talk about a few things that we've developed as kind of best practices for iterating on Fortnite. So first up, distributing the editor. Back in the UE3 days and on the early days of Fortnite, we had this process which we used to call the editor promotion pipeline. We'd have our build machine sync down the latest code, then update a header file with the changeless number that it synced, compile the binaries, then submit them to Perforce. Our QA team would sync those down, test them. If everything went well, they'd apply a Perforce label to it, and our artists could sync that down using a little desktop tool that we made for them called UnrealSync. I just want to dwell a moment on the bit at the start of that, when we update the version number. That's not just a cosmetic thing. That's actually a really important thing for avoiding data loss. Unreal's property serialization is really useful for rolling development, where you can modify class layouts whenever you want to, and you don't really have to worry too much about upgrade paths. If the engine encounters, if you've added a property to a class, then and an asset was saved out without it, it'll just be initialized to its default value on load. And if you remove a property, it will just skip over it in any data it loads in. That can cause a problem if you load up a new asset with an old editor. It's not going to understand some of the properties that are serialized out to it, so it's going to discard them. So to avoid that, we compile the changeless number into the editor, and we can tell the editor to refuse to load anything that was created in a newer version than itself. So this is what the kind of cycle would look like on that pipeline. We'd have a build, we'd test it, then the QA department would bug it, and then it would go into the triage queue in our bug tracking software. Hopefully, the lead of the team that it went to would triage it quickly. They wouldn't be in a meeting. They wouldn't be out to lunch. Then it would go to a developer on that team. Hopefully, it went to the right person straight away. They would try and reproduce the bug and then check in a fix for it. We really struggled to make this scale to Fortnite. As the size of the engine was growing and the number of people who were working on the project grew, the amount of test area there was for the engine was increasing and increasing, and the likelihood of finding a bug was getting more and more. Once we completed one of those cycles, which at best would take half a day, and at worst could take a day or two, then we'd have to run the cycle again. By the time we got to the second time round, there was a good chance that somebody else had submitted new changes which had broken something. And so we'd just go round and round and round. We're getting to the point where it could be up to a week before we'd get promoted binaries to our artists. Back in the early days of Fortnite, when we were dealing with this, we were still struggling to figure out exactly what the project was going to be. And so that loop, that iterative loop between gameplay engineering and design was really important. The fact that blueprints serve to sort of enforce that mentality that you kind of have to work lockstep together to figure things out was really hurting us and slowing down our progress on the project. That wasn't the only thing, though. The fact that we were checking binaries for artists into Perforce was creating problems with our engineers because they were syncing them down and getting mismatches between binaries they'd built themselves and binaries that they were syncing down from the build system. Sometimes there's they try and mask that out with their client spec in Perforce. And sometimes they get it right, sometimes they get it wrong. When you end up with a mismatch, if you're lucky, you get a dialog box from Windows, which isn't very helpful, saying that it can't find a symbol or something like that. If you're unlucky, then everything looks like it works fine, and then you just end up with some random memory corruption because class layouts are different in different modules or something like that. What's more, it meant that engineers couldn't check in any content. If they needed to change content, they'd have to check in their code changes, wait for an editor to be promoted, and then make the content changes. If they tried to check in things they'd made with their local build of the editor, those would be unversioned, and any artist who was syncing them down with the promoted version of the editor could wipe out any properties they'd added. So while we were trying to figure out how to make this scale how to figure out how to solve the promotion problems for Fortnite, we had a small project starting up called Battle Breakers. It was a team of 10 people, a mixture of artists and designers and engineers, and they all sat in the same room. They were really passionate about their project, and they really wanted to make it succeed, and they didn't really care about process and things getting in their way. So this whole promotion pipeline didn't work very well for them at all. They decided that they would solve it by just turning everybody into an engineer. They gave everybody a copy of Visual Studio Express and taught them how to sync from Perforce, generate project files, load up the solution in the IDE, and then build their own editor. And it kind of worked for them. In fact, it worked really well for them. If they ended up with a problem, there was a compile error or a bug in the editor or it crashed or something like that, they just turn around to the engineer who was sitting next to them and ask them to come and have a look. That wasn't such a big deal for the engineer because they already had Visual Studio installed. They had full symbols. They could just debug it there and then and get the artist back on their way. It also had a really positive side effect that we didn't anticipate, which was that by making communication between artists and designers and engineers the norm and like part of their daily workflow, they'd also get a lot more feedback on things that would really contribute towards improving the product or just hardening the editor in general. Any workflow things they wanted, they'd have an avenue to communicate them. So we thought, could we scale something like this up to working on Fortnite? We went into this with a bunch of concerns about how to get it to work. The first one was stability. Obviously, stability is going to get worse because nobody's checking the editor anymore. But who is that really going to affect? For artists, they're usually relying on core workflows that are part of the engine that gameplay engineers aren't changing too much. So on a game project, they're probably going to be pretty stable. For designers, there's definitely a trade-off there, but it was a trade-off that they were willing to make for sacrificing stability for a bit of productivity. And there was also a bit of a case to be made for the fact that designers are testing the more relevant code paths to the game anyway. So QA might be bugging things that they have a test plan for that was decided 6 months ago. Designers are always on the cutting edge and trying the things that are actually in the game right now. We're worried about data integrity as well. There was every possibility that somebody could check in a change that would just format somebody's hard drive or something like that. We had a look back and sort of issues we'd seen before where somebody had checked something in that had caused assets to be corrupted or something like that. We didn't want anybody to lose work. And we figured that that sort of content corruption was actually really rare, and it was usually a kind of insidious thing where people in QA didn't see it when they were running their test plans. There would be a lot more versions of the editor in the wild if we did something like this. People could build their editor at any arbitrary change list. So that problem with versioning for property serialization is still something that we're quite concerned about. Finally, compile times. Nobody really wants to compile unless they have to, but we figured that it might be worth trying. There's still the practical matters of getting all this stuff to work, and we figured that we didn't really want our artists having to load up Visual Studio and being faced with all of the toolbars and menus and ability to do the wrong thing. So we decided that we wanted a one-click workflow that was going to work for them. We also knew that because we didn't have everybody sitting in the same room, we'd need a way to surface information that other people could see, how to communicate issues between the team. And this is what we came up with. This is our little prototype of a tool called UnrealGameSync. It's a little bit of a noisy screenshot, but you can get the basic idea of how it works. You have at the top there, you select a project on your hard drive, then it will detect the perforce settings that go along with that project, which workspace you're using, and so on. And then it'll fetch a list of all the changes which have been checked in that affect that project. You can select anything from that list and double-click on it, and it will sync it down and compile it, and then launch the editor. If it compiles successfully, it sends a little event to a database, to a web service, and that shows up as a little green dot for you and for everybody else on the project. If it fails, it comes up as a red dot. If it does fail, or there's some problem with the editor and it crashes at startup, or there's some blocking issue with it, you can come back to the tool later on and right-click on one of the changes and mark it as bad. And you can also leave a comment explaining why you did so, like give somebody some idea of where to start looking for the problem. And engineers would use the same tool as well, so they could sync down the code. They don't have to compile through it if they don't want to. They can just compile through Visual Studio. But this is going to take care of updating all the versioning information for them. If they are investigating an issue that somebody else has flagged as being wrong with the build, they can mark the build as being under investigation, and that'll show up as a message in that column on the right there saying the name of the person is investigating the build, discourage other people from syncing it. This all felt like a really bold experiment. Fortnite wasn't a small team at the time. And in order to get it to work, it would require quite a culture shift. But we figured that we didn't have much to lose about it. The process that we had at the time was pretty slow and cumbersome, so we figured that we'd give it a go. And one weekend, IT installed Visual Studio Express on all of our artist machines, and we came in on Monday morning and just started using it. And kind of surprisingly, it was actually really successful. We got a lot of feedback on it, and we iterated on the tool quite a lot in the early days. One of the first features that we added was the ability to set up a schedule so that you could sync a build overnight, or you could sync down perforce overnight and make a build from it, so that when you get into the office in the morning, you'll already have an editor there for you. And it very quickly became a staple of our workflow. We regarded it as a big win for Fortnite, and it really helped us get back to that rapid iteration cycle that we wanted. That was 4 years ago, and we're still using UnrealGameSync now. This is what it looks like today. Pretty much the same kind of general look to it. We've polished it a bit and added a few extra features, like now you can have multiple tabs so that you can see different projects open at the same time. There's a big status panel at the top which shows you what you're synced to, allows you to open some really useful tools, like, and also show you things like which SDKs are required in that branch. It also allows you to switch between streams. We found that perforce fast stream switching has a bit of a bad reputation because of how easy it is to do it incorrectly, but being able to expose it through a tool like this allows us to hide all the nuances and do it reliably. The main panel is pretty much the same, but the obvious difference is all of these badges on the right, these green badges. Fortunately, they're green because it's a good day today. These are results from our build system. We realized that having a tool like this that everyone was running made it a great choice for something that we could use to surface information about the state of the build, notifications from the build system, and so on. Those badges are really easy to add and completely customizable. There's a little command line tool called PostBadgeStatus that you can pass with a bunch of arguments like the name that you want to appear on the label, which change list it's for, whether it succeeded or failed or produced a warning. And you can give it a URL to open if the user clicks on it. We usually use that to take you to a build log or something like that so you can investigate more. Because UnrealGameSync is also polling for changes that are being checked into the branch in the background, it also knows when you've checked something in. And if one of those badges turns from green to red, it can give you a little desktop notification, tell you that you might have broken the build as well. We put a lot of attention into what we build as part of our sort of continuous build cycle to get good feedback on those badges. And this is what we build nowadays on Fortnite. Every 10 minutes, we have this build that starts up, that builds the editor incrementally on one machine. So it's fast because it's only compiling all of the changes. It's built in non-Unity mode so that any CPP change only has to build that one file. It doesn't have to rebuild a whole Unity blob. And it also means that we catch things like missing headers. Once we have a compiled editor, we run a little commandlet, which just loads up any contents which has been changed since the last time it was run. It doesn't do anything with it. It just loads it up. We found that when we were making our packaged builds of the game, the most common source of errors was artists who'd forgotten to submit a piece of content. So just by loading it up, it causes the editor to output errors and warnings if something's missing. And we can surface that through a badge in UnrealGameSync. The next thing that we do is to run a quick automated test that just spawns the editor twice, once with the dash game argument, once with the dash server argument. Just checks that a client and server can talk to each other, check that the login flow and matchmaking process works correctly, checks that you can make it into a match, and then checks all of the 4 basic actions that you can do in Fortnite. Checks that you can move, checks that you can shoot, checks that you can build, and checks that you can harvest. And we have a second machine which incrementally compiles the game for all of our target platforms. Those are just 2 machines that we have running all those tests, and it's a massive, massive value for us. It's a really nice balance between getting quick feedback and getting broad coverage of things. Paragon was the next project which used UnrealGameSync. And Paragon was a project that ramped up really quickly and had a really large art team and a really vocal art team as well. They did not have the history that we had on Fortnite of trying to iterate for a long period of time. They just wanted to get stuff done. They did not know why they had to compile stuff at their desks, which is a reasonable thing to complain about. So they wanted to go back to a model where binaries for the editor were built in some centralized location, and we could distribute them out from there. We didn't want to go back to the situation where we were checking binaries into the source tree and all the problems that we had with churn and engineers syncing down binaries and getting mismatches locally. So we decided to go for a system where using the same kind of using the binaries that we're already generating as part of our continuous integration tests, we'd just zip them up and we'd submit them to a location somewhere outside the branch. UnrealGameSync could then, if the user chose to enable them, could fetch those binaries without having to create a workspace for it. You could just get that one file and use the description on that revision to match it up to which source change list it corresponded to. That was a really nice solution because it allowed us to get all of our departments using exactly the same tool for syncing binaries. For the case where people were using precompiled binaries, it would just show changes which didn't have matching binaries grayed out. And for everybody else, they could sync and compile whatever they liked. A quick tour of some of the other features that we have in UnrealGameSync as well. It was kind of frustrating when we switched from old-style Perforce workspaces to streams where we couldn't customize what everybody was syncing. When people are working from home or they have a poor connection or something like that, syncing down lots of stuff that they don't care about was a waste of bandwidth and was making syncs take a really long time. So at first, we tried to solve that by creating virtual streams for things. And that works OK if you just have one or two of them. But we're finding that the number of permutations that people would want was getting out of hand. And the number of branches was increasing as well. So people would want their own personal customizations on every single branch. So we decided to sidestep perforce and just do all of the filtering on the client side instead. Since everybody's syncing through one tool, we can build it into that. And it allows us to create a much nicer user interface around it as well. It allows us to set up some broad, high-level categories that people can choose from, like an a la carte menu of things that they want to sync. They can exclude certain platforms they don't care about. Maybe they don't want cinematics content or something like that. Or they don't want localized assets. And they can all do it from inside this panel. We also added this clean workspace tool, which kind of serves two purposes. First of all, to clean out any intermediate files that you have. The directory layout that we have in UE4 means that things like plugins and game projects, things can be scattered all over the source tree. So something like this allows us to clean up those intermediate files. And it also allows us to check that you haven't deleted any files that are in perforce, or you haven't made them writable even. So it gives you this nice tree view. You can see everything that it finds. And it will only select things which are known intermediates by default. So it's not accidentally going to delete any work that you've created and just forgotten to check in. Unlike the p4 clean command, this only checks whether files exist and the attributes on it, whether it's read-only or not. So it can execute really, really quickly. It takes about 10 seconds to come up and compare the whole workspace. Our QA department uses UnrealGameSync as well. So we added this feature for them so that they can regress a bug. If you hold down the Shift key, you select a start change list and an end change list, and then right-click on it. You can go into this Bisect mode, which allows you to, which filters down the view to just include the changes that you've selected, and then you can mark individual changes as good or bad. There's the sync button at the top, changes to saying sync next, and it will sync to the middle of the range between the last good and bad change. So it allows you to do a binary search for the change that introduced a bug. Finally, we added a lot of little customizations that were useful for our own projects. This is what a recent Fortnite release branch looks like. You can see it's got the Fortnite logo there. And we also color the status panel red so that people know that they shouldn't be working in there because the branch is locked down. There's a little message of the day feature underneath the status panel just there, which usually gives you like some information about the dates that we're going to branch. Also allows you to get a link to your list of bugs in our bug database, that kind of thing. I've kind of grayed out all of the changes descriptions, but next to it you can see these little buttons here. We have a perforce trigger that requires everybody to include a bug number in all of the changes they submit. And in UnrealGameSync, we can pass that out using a regex and create these little badges for it. If you click on that, it'll take you to our bug tracking software, to that particular bug. All of this stuff is configured through config files. We don't have any epic internal special version of UnrealGameSync. It's all config file driven based on config files that are checked into the branch, so any project can do whatever they like with it. The latest source code for UnrealGameSync is in Perforce and GitHub, so if you're interested to give it a try, I'd thoroughly recommend that you do so. It's not locked to anything in the engine itself. In fact, we distribute it as a tool outside the engine, so it's not synced down as part of the branch. So if you want to try it, then you can always go to the latest UE4 release and take a look at it. And there's more information about setting it up on our docs site. Next up, branching. The engine team was the first team at Epic to try out Perforce streams. And we adopted a lot of the best practices from the Perforce documentation. We have a kind of branch hierarchy like this, where more stable changes exist at the top, and unstable changes and development work goes on at the bottom of the hierarchy. And those changes merge down. Whenever we've done some work in a development stream, we're ready to copy it up for a release, then our QA department tests it, and then we do a copy into main. We try and keep main pretty stable. And then whenever we're coming up to a release, we want to stabilize it, then we create a new release branch by branching off main. This kind of model works really well for code, but it works absolutely abysmally for content because you can't merge assets. So for Fortnite, when we switched to streams, we started off with a kind of model like this. We'd have 3 branches, the mainline branch where most people would work, then a release next branch, which was used for stabilizing the next release, and a release live branch, which reflected what was currently live. If we wanted to do any hot fixes, we could do it in the release live branch, and release next would give us a bit of a window to stabilize before the next release. By reducing the number of branches, we reduce the number of places you can create conflicts. But this model was not without its problems. First of all, the fact that we only have 1 release branch means that it's very easy to get pipeline bubbles. If for some reason the build which is in release next gets held up by a few days and can't be released to live because we find a bug or something like that, then that means that we also can't vacate release next and copy up from main. There's kind of like a big confusion there because people never know quite what is working, what work is in which branch. They don't know where to do their own work. They'd have to really track the release schedule to understand, and any notices, the emails that come through about delays and things like that, to understand where they were supposed to be working for something. There's also a weird artifact in that we never know quite which build we're going to release until it's been approved by QA. So we're constantly testing builds that are made out of release next, and then finally they give the thumbs up to it, and then we copy up into release live and release the build that was made in release next. That means the first time that we actually come to do a hotfix in release live, it's the first time we've exercised all the code paths for running that build out of that branch on our build system. It's not the time when you want any kind of delays. After a while, we switched to this kind of model, and this is what we're using nowadays. We create a dead-end branch for each release. It's numbered so that people know exactly what it is, and artists use fast stream switching to switch between them. We have a major release coming out every 2 weeks or so, and we figured that it takes us about 3 weeks to stabilize each one. Sometimes it's a little bit longer for the first release in a season or so. This kind of model gives us lots of flexibility for creating as many out-of-band releases or any special releases that require extra time to bring into land. We still have plenty of problems with conflicts being created in release branches, though. We used to have a situation where when we had we would have an engineer who would get the unlucky job of having to merge down from a release branch at the end of a day. And there would be all sorts of conflicts that he'd have to figure out how to resolve. And he'd reach out to people and try and negotiate which way it should be resolved and things like that. But more often than not, that resolution would involve accepting one side of the changes, one of the changes, and then redoing some work. So until that was done, that meant that what was actually in the branch was broken. So we made this tool, which we called RoboMerge, that would automatically merge things down from release branches into more stable branches, into more unstable branches. It would do it change list by change list. So if there was any conflict, it would know exactly who to blame. It would be the person that submitted that change. And it would also do everything in order, so it wouldn't cause conflicts later on because one change has been accepted over another. RoboMerge really helped us identify conflicts quickly, but it didn't do much to stop us creating conflicts in the first place. So we added this functionality to the content browser, which allows us to check multiple branches, check the state of assets in multiple branches at the same time. In the screenshot on the left, you can see that it's showing an asset that's checked out by somebody in another branch. And in the screenshot on the right, it's showing that somebody has already made changes to that asset in a different branch. Because it knows that changes in a release branch are going to be merged down into the main branch, say, it can check to see whether somebody's already changed it in the main branch. If it has, then that's going to be a conflict waiting to happen. In both cases, it'll give you a big warning dialog saying, you're going to screw somebody over. Don't do this unless you really know what you're doing. Sometimes it's necessary for fixes that are going to an existing release that you kind of don't mind dead ending. You don't care about it being merged down or anything like that. You just need to fix it in live. But usually it's something that you want to try and avoid. That functionality is in the base engine, but it has to be set up by code. This is what the code to do that looks like. The key function there is iSource control provider register state branches. We typically call this from, we have a Fortnite editor engine class, and we call it from the init function of that. You just call register state branches with a list of branch names and a relative path to the content folder within it. Doing it from code is really convenient because it allows us to determine the branch topology dynamically. In our case, because we have RoboMerge set up, rather than hard-coding a list of branch names, we just read the RoboMerge config file. So whenever we create a new release branch, we only have to update it in one place. After spending a while talking about how horrible binary assets are for us, it would kind of be remiss of me not to talk a little bit about text-based assets. We've been working on this for a while, on and off. And we've made progress on it. There are traces of it in the engine today, but it's still not quite ready for prime time. It's a pretty gnarly thing to retrofit because there's so much serialization code already in the engine. But we have a plan for it, and we think it's going to scale up and allow us to create a good upgrade path. The idea is that we create a new archive type, which we're calling structured archive, fstructured archive, which allows serialization code to add additional annotations for structure and the naming of properties. Creating a separate archive type means that we can change the interface a bit, make it so the compiler can statically check things, also put some validation code inside the archive before it gets to the underlying archive, so that we can check to make sure that, for example, if you're starting an array, then you're also finishing the array, and everything is scoped correctly and things like that. The goal is to have that archive be able to write out to 3 different backends. The first would be raw packages, exactly the same packages as we have today. Hopefully, that would be the intent to make it so that's completely compatible with the current binary format of packages, so that you can load existing assets without any problem. The other backend would obviously be text file format. And the third format would be a kind of intermediate format that would help us make it so the editor can start quickly. It would be a kind of binary version of the text-based asset, would retain all of the annotations, unlike the raw package format. That's kind of useful for things like the asset registry, which needs to scan all assets and pull out metadata about the import tables and stuff like that. We can pre-compute those and cache them. The idea is to make all of this structured archive stuff completely optional, so that you can compile it out in your finished game. You don't have to pay any of the overheads for tracking any of this metadata. One of the things that we've learned about it already, though, is that just because it's text doesn't necessarily mean that it's mergeable. Obviously, things like textures, if they're stored in a text-based format, you don't expect them to be merged. But one of the high-traffic things that we have in the one of the high-traffic types of asset we have right now are blueprints and UMG widgets. And those kind of things are really difficult to merge anyway. Because they're node networks, then it's very easy to change the topology of it by just creating a new connection. And when you serialize that out, then it results in everything moving around across the file. It's also really easy to just select a bunch of nodes and just move them right by 10 pixels and change hundreds of places in the file. So we don't expect this to be a panacea for merging assets, but we do think that having the visibility into what's in an asset is going to be useful. And by improving our data structures over time, we're going to make a lot of that stuff kind of easier. It's going to require a lot of work and a lot of changes to existing systems, though. So we've got to start somewhere. The last thing I wanted to talk about was iteration, some of our best practices for iteration. This is a little bit more scattershot than some of the other 2 categories that I talked about. But I think some of it is valuable, and there isn't really a good place that you might otherwise find out about it. First, on Fortnite, we invest heavily in working in Play and Editor. Most of our artists and designers work in Play and Editor, so do most of our engineers. For a multiplayer game, it's quite convenient. You have the ability in the drop-down menu next to the play button. You can choose how many clients you want to spawn, whether you want a dedicated server or not. And we end up with most of our development work happening in the full map. We have a few test maps for isolated bits of things that we want to test, but most of the work happens in the full map. We've also made an effort to support full integration with our back-end services through Play and Editor. This is kind of a little bit tricky because it means that we kind of have two separate code paths for it. But doing so means that we can test anything in Play and Editor. We use real accounts. We can log into the game. We can test the whole login flow and matchmaking system and design all of our UI and test it right there and then. Worth mentioning as well that I mentioned it a little bit before, but worth highlighting that being able to run the editor with -game or -server to use uncooked content is a super useful way of being able to iterate on code without having to launch the editor. Next up, the cooker, everyone's favorite waste of CPU cycles. The main loop in the cooker just consists of loading up packages, inlining derived data, and saving them out again. Derived data is the platform-specific version of, say, a texture or a shader or whatever needs to be pre-computed to run on that particular platform. Creating derived data is usually really slow. Things like computing PVRTC textures is incredibly slow, but it's also very it's completely deterministic, and it's very well-defined in terms of a transform. You know exactly what the inputs are. You know exactly what the outputs are. Hardware is designed to decompress it, so the format isn't going to change. It's usually really stable over a long period of time. So what we do with derived data is to cache it. By default, it's cached in a local folder on your machine under the engine folder called derived data cache. It means that the next time you run the cooker, or even when you run the editor, because running on the editor is running on your host platform, you have to create platform-specific versions of PNG textures for that. Next time you run, it's always going to fetch it out from the derived data cache. If you're working in a team on a project, then setting up a shared derived data cache is really valuable. A shared derived data cache is just a network folder that everybody can access. If something's in your local derived data cache, it will get it from there. If not, it will go and get it from the shared derived data cache. If it's not there either, then you'll do all of your teammates a favor by making it locally and then pushing it to both levels of the cache. The one time that we find derived data to be really volatile is shaders, because you can create new materials. Shader compilers are upgraded often with SDKs and things like that. And to recompile all the shaders for your game can take a really long period of time. For that, we use IncrediBuild or XGE, the DevTools package. We can run the shader compiler through that and parallelize it out over a large number of machines. So that's the main way that the cooker runs in parallel. For most builds, especially builds where everything's already in the cache, then it doesn't run very parallel at all. It's bound by CPU performance and being able to load up packages and save them back out again. Loading and saving is done on the main thread. So that means that if you're looking to buy hardware that's going to be good for cooking, then you want something that's going to be fewer, faster cores rather than large number of slower cores. In terms of optimizing that, the obvious ways to do that are to just load and save fewer packages. For our games, we have a few special modes that we can run the cooker in, depending on what you want to test, which filters out the packages which the cooker is going to consider. You can do that through registering a cook modification delegate. The other thing that causes the cooker to load up more things that it would need to is if it's already purged, it's loaded that package before, but it's already purged it from memory. The cooker is eventually going to spider through every single package that's in your cooked game. And as part of doing that, it's going to have to load up each one of them and resolve any references to other packages. References in Unreal are stored as object pointers, so it's actually going to have to instantiate all those other packages as well. We don't expect that many games will be able to fit in memory all at one time, so periodically we have to run a garbage collection, which will discard things. But there's a good chance that some of the things that's discarded will also be referenced by other things in the future. So to limit the amount of times we run a garbage collection pass, you can set the max memory allowance config value in default engine.ini, default editor.ini, sorry, to something higher. It defaults to 16 gigabytes, so as soon as you hit that 16 gigabytes working set, it's going to run a garbage collection and get rid of everything. If you have more memory on your build machines or on your developer machines, you'd increase that to something much higher. I'd like to be standing here able to tell you that there's some secret magic trick that I can exclusively reveal today, which is going to make working on device with UE4 a lot easier than it is. But we don't really have one. It's pretty rough. We know about it. We are working to improve it. There's just a lot of legacy there, and it's taking a while. One of the things that we're talking about doing right now, or we're actually experimenting with doing, is what we're calling shared cooked builds. The idea is that you'll copy a build from a build machine that's already cooked and packaged and stuff like that, and then you can just get your local changes, your diffs from that build, and cook those locally, and then add them on the top. That makes the cook times for it a lot quicker. One of the things that we are having a lot of success with is Gauntlet. Gauntlet is a command that's part of automation tool that we use for running our automated tests. It actually kind of does more than that, and you can use it locally for kind of test scenarios and just to sort of set up complicated deployments. It can take, for a sort of defined scenario, it can spawn like a server and 4 clients on different devices, communicate with them all, get them all to run a certain command, and then harvest data from all those devices, bring it back to the host machine, and generate reports for it. We use Gauntlet a lot for performance testing, regression testing as well, especially. We can run, we use replays to reproduce exactly the same gameplay scenarios from a live match over and over again, and we can get a sense of whether performance is improving or worsening over time. Gauntlet is pretty badly documented right now, but we are hoping to have better documentation for that in 4.23. We've had hot reload in UE4 for a long time, and it's great for marketing materials, but on real-world projects, it kind of falls a bit short. It relies, or it makes some pretty big assumptions that all of your game state is going to be captured by the Unreal reflection mechanism, so that it can load a second copy of your game DLL and then transfer all the state over to it. That's not usually true for big AAA projects. As soon as you introduce a global variable or a native singleton or something like that, then hot reload is kind of dead to you, unless you jump through some hoops to make it work. So a while ago, our engineers on Fortnite started trying out this commercial product called Live++. Live++ is works in quite a different way. It works in a more fundamental way. You compile a bunch of object files, and then it will actually link those into the running process. It means that whenever it resolves a symbol to a function, if it doesn't have a new version of that function, it can call the original one that was in the process. If it has a reference to a global variable, it can use the initial one and its current value. Similarly, any functions that already exist in the process, it can patch those, do a long jump to the object file, and use the replacement versions. It's really quite awesome when you try it, and it's quite a transformative tool. For our workflows, like I said, we work a lot in plain editor. That means that you can load up the editor once and keep a session running for hours, just constantly making changes to it. So we've integrated. We like Live++ so much that we licensed it. It's now part of UE4. We integrated it as a feature called live coding, and it's in the 4.22 release. It doesn't support layout changes right now. You can't change class layouts, but that is something that we're working on. Finally, iterating in prod. we work on a there are always things that will escape the testing net, and you'll only discover when it gets into the hands of players and you're running at scale. That can be bugs, it can be exploits or glitches, and it's quite difficult to deal with those things. It's always a scramble. One of our mandates for any new features that we add is that everything can be disabled by a config file value. Not only disabled, but everything can be tuned as well by config file values. It kind of means that once we have our build locked down, we can still maybe iterate with the settings and stuff like that. That's done with a class called Online Hotfix Manager. It requires an implementation of the iOnline title file interface, which is what provides it the files which are on your backend or on your sort of backend service platform or whatever. The idea is that, in our case, we can upload a bunch of config files that we want to patch the game with to our servers, and then at the start of the match, it'll sync them down and apply them there and then. Through that, you can change a bunch of things. You can change properties, console variables, or if you have code which just queries the property value every single time, it'll also be updated. And you get a notification called if you want to update things based on those properties changing. Thank you very much.